In this session, we are going to talk about the block diagrammatic representation and how are we going to draw the block diagrams and what is meant by block diagrams and how do we minimize the block diagram, and from the block diagram how do we make the transfer function. So the topic is block diagram. So as I was telling in my earlier session, you may feel it is a little bit laggy because I wanted to ensure that every one of you should understand in detail whatever I'm going to talk about. So generally, a block diagram is a pictorial representation of the functions that is performed by each component. So like for example, I'm just telling you one small example here. Suppose this one I'm just putting into a small box. This one composed with the input. That input is say A, and the output is coming as B. So the entire information is there in the block in the form of a transfer function that is called as a g of s. So that is how the block diagram is represented. In the block diagram there are so many parameters such as summing point, branch point, and all those things. So now let us simply draw a block diagram, and then you can understand how this is exactly is being drawn. So here, for example, let us take an example, that is our motor example. VA is equal to IA RA plus LA DIA by DT plus EB, where the torque is also represented is equal to KT into IA. That torque also can be represented as T is equal to Z d omega by dt plus B omega, and the back EMF EB is equal to KB into omega, where omega is equal to d theta by dt. So this is the entire system that we wanted to represent in the form of a block diagram. So let us take one by one step, and how do we draw. So here taking on the Laplace transforms for the V of s, we were already getting, we already got the information such as VA of s is equal to IA of s into RA plus LA s into IA of s plus EB of s. So from this VA of s, let me take rearrange the equation. VA of s minus EB of s is equal to IA into RA plus SLA. So from here the output IA is equal to VA of s minus EB of s divided by RA plus S into LA. So it is very simple. Now our aim is here very clear. We are giving input as VA, okay, and that VA is getting subtracted with the back EMF, that is EB, that is VA of s. I'll write EB of s, and that is coming out as 1 by RA plus SLA. See how clearly it is. So this IA of s, this is called IA of s. IA of s is equal to this particular block multiplied by V of S minus EB of S. Okay, so from this particular block, what we need to get is, for the IA of S, this is one particular block. For the let us draw the block by block. For the torque, how are we trying to do it? So for the torque, we are giving, so firstly let us write this torque T of S. T of S is taking the Laplace transform KT into IA of S. So here, when you are giving IA as the input, the torque is multiplied with KT. So that means what is happening here? Whatever the torque that you are getting as output by giving the current, that T of S is multiplied with KT, having the input is IA of S. Similarly, the torque, the equation, another equation, if you write this equation, T of S is equal to J ES into omega of S plus P omega of S. That is equal to, if you take omega S as a common, J S plus B, when you take omega of S as a common. So from this, that T of S is equal to Js plus B into omega of S. So from this omega of S also you can write omega, where the twisting moment of force is the torque, omega is equal to 1 by Js plus B into T of S. So for this particular block, again I can write as, so the omega, the output is omega. Omega is, whenever you are giving torque as the input, if you multiply it by 1 by Js plus B, then automatically the omega is coming. Similarly, the another last this thing, so the another one is EB here. So what is EB? Back EMF. EB of S is equal to KB into omega F. So these all equations I taught in my earlier session 4 or session 5. Please look into that, otherwise you will not understand. So from this, when you give omega as the input, omega S as the input, if you multiply with KB, you will get EBS as the output. So that is how you will get. And finally, one more thing is there, omega is that. So here, omega S is equal to S into theta of S. So if you take theta of S is the output, so for the theta of S, omega S as the input, theta of S is equal to 1 by S, right? So omega S as the input, 1 by S, if you integrate, you will get theta of S. So taking all those things into consideration, one by one, if we draw a block diagram, so the first thing that we have written is, that is VA of S, that is VA of S minus EB of S gives rise to 1 by RA plus ESLA in, that is equal to IA of S. So KT is equal to, this is IA of S. IA of S into KT gives rise to T of S. So this is the arrow, this is how it is flowing. This KT, this T of S is multiplied by 1 by Js plus B, then you are getting omega of S. This omega of S has two things. Omega of S is equal to KB into omega of s into KB is equal to EB of s, and the same omega f of s, if you integrate with 1 by s, you will get theta of s. So this is one sort of a transfer function that we are trying to put, that is block diagram of a armature controlled DC motor. In this armature controlled DC motor, what is happening? In fact, you are giving voltage and you are getting speed, the angular theta as your output. So we can take anything of any way that you want for different kind of block diagram and all these things. Okay, and some sort of rules that I'm just telling you in block diagram. This is how we can draw the block diagram very simply, and the block diagram of various types can be reduced into proper reading fashion. Suppose you have a block something like this. Say block Z1 is there, and if you are getting some sort of an input, so A is multiplying with Z1, you will get A into G1. Suppose this is multiplied with another block, say G2. So AG1 is coming in cascade with G2. This output will become A G1 G2. So this can be written as how equivalently can be written. If I have a complete block diagram as G1 G2, and if I give as input A, the output also can be written as A G1 G2. So this is equivalent representation. So that is how you can make like lot of things. Say for example, you have one more function, same thing A, let us assume, and let us assume that you have an addition block here. Generally the summation can be represented in the control system something like this. So suppose you have here G1 and this is say A. Now as per the above things, A into G1 will become A G1. Say for example here A G1. Similarly, suppose there is one more block here, say G2, and this you are giving as the input. Then what will happen? A is multiplying with G2, this is coming and adding here. This will become A into G2. So what is the output here? Output is the summation of A into G1 plus A into G2. So this also can be written as simply, suppose if you have a block of G1 plus G2 and you give a input as A. So what is the output that you can get here? A into G1 plus G2. If you multiply and separate, A into G1 plus A into G2. So likewise also you can get the kind of system, different kind of system transfer functions you can get in a different way. So this is called a block diagram reduction. So there are so many moving away the point, in summing the, so there are so many block diagram techniques are there. I don't want to enter into detail about it, but we will solve some sort of an example where you can understand those things in a very clear cut fashion. Suppose let me take one simple example. Okay, in this simple example I have a block. This block says G1. This block is connected to another block. Say this is say G2, and this is connected to another summation block, that is say plus here, and say I'm taking this as the output C. So for here, so I'm also taking input. Say this is the input R I am taking. So this is the plus. This R I am directly giving to G1, and this is the minus, this is taking as H. Okay, so this like this, let me assume, and let me, if you want to make it more complex, let me add one more term, that is say G3, that I connect to this particular G3 point and add it. So it may be, say let me take this also plus. Now I want it to brought down into single transfer function, something like this. How I wanted to bring it down here is R as a input, and it will be a block diagram. Okay, so this is completely like complete transfer functions as G, and this should be C. Now the output by C, so see here the C is equal to R into G. So C by R is equal to G. That means output by input is your transfer function. I want to bring into this fashion. Now how I can bring that into that particular fashion? So let me think into step by step. First of all, what I'll do, this point, whatever this point is there, if I transfer this point to here, then this will become a completely a feedback path kind of thing. It will be easy to understand that, right? Or you can also do this, you can also bring this point to this also, then you can become these two in cascade. So either of them, see, in a block diagram reduction technique you can do anything that you want. Okay, suppose what is happening here, suppose this particular point here you wanted to bring from this to here. When you put this particular point here, the effect of G1 will come into picture. So the effect of G1 we have to remove. To remove the effect of G1, what we do here is very simply, so same thing I'll write, this is say R, and here what the, where I'm transferring this, only G1 will be there here, and here when I'm transferring this particular point to here, effect of G1 will come into picture. So what I will do, I will divide the effect of G1 so that whatever the effect of G1 is coming, that is nullified. Is very simple from here. So earlier the effect of G1 was not there. When I am shifting here, the effect of G1 is coming into picture. So the effect of G1 I am just removing by dividing with this. That simple it is. Now here C2 is there, and there is a summation block that is happening. This is plus, this is plus, this is C, and this is plus, this is minus, and this is coming as H. Now this is very simple. It is a kind of simple feedback path. It will become G by 1 plus GH, and here this I am writing as very simple, that is this one. So R is coming, this already we have derived, G by, because it is in the negative feedback, 1 plus GH, this is already coming. Now here another block here is coming, this and this are adding. Okay, here I am just adding these two, G3 by G1 plus G2, these two are adding together, and C is coming. Now all are multiplying with each other. That simple it is. So when you are trying to build this thing, you have to make it very simple. So now this is in 1 and this is say in cascade form. So we have to multiply G1 this is G1, G1, G1 by 1 plus G1H into G3 plus G2 G1 divided by G1. So this G1 out. So finally what you will get? G3 plus G1 G2 by 1 plus G1H. That's all. So this complete two blocks will be replaced with this particular block. Now finally what you will get? Single block. What will get single block? Here it is. So R as the input, C as the output. This transfer function will be sitting here. This type of technique is called the block diagram reduction technique. So this can be elaborated to any sort of big example. So we'll take one more example so that you'll have complete clarity in understanding. Suppose again let me take G1, G2, G3, G4, H1, H2 like that. Let me take a big block diagram. Okay. So let me take the example number 2 in the block diagram reduction technique. Say for example I have G1 block is there. This G1 block I am connecting to a particular summation block which is having plus and minus, and from here there is say one more block that is there, that is say Z2 is coming. From the Z2 say there is one more block that is going here, that is say G3. From the G3 you can take a summation point here, this plus, and you can take one more plus summation point, and you can take this as the output C. Okay. For the input, so let me take in between we'll take here one feedback path. Let me take this feedback path I am calling as say H2. I am taking directly from the output. Okay, from the output I am taking one feedback path. To make it more complex, let me take one more feed forward path. This I'll name it as G4, and this one I will add it here. Okay, now from the mid of G2 and G3 I'll take one particular path. This one I am calling as H1. I'm calling as H1. This one I will add here, say plus minus I am adding here, and again say one more path I'll take plus minus. This one I'm calling as R. From the feedback path here I'll take directly from here, and this is connected here. So likewise what is happening, you can have so many block diagram reduction technique for the closed loop transfer function whose block diagram is shown here. So this one we wanted to reduce as we have just discussed that in a equivalent fashion. Here R as a input, C as a output. I wanted to bring this entire big block diagram into single box as this. This is what we are trying to do now. So one important thing that you already know, that if it is one feedback path is G by 1 plus GH. So that those things are very clear to you. Now let us go into one by one path to make it very simple. Suppose firstly if I transfer this to here, here the effect of G2 is coming. If I transfer this here, the effect of G2 will not be there. So what I will do, if I transfer from this point to here, effect of G2 will not be there. So for this, if I multiply the effect of G2 here, that will be solved. So what I'll do simply, this one I am transferring it to here. So I'll take another color. So this one I am transferring it to here, and when I am transferring this here, this particular one is coming here, and the effect of that is coming into picture. Okay, so when I am transferring this to this particular point, the G2 effect was there earlier, now it is not coming, so I am multiplying the effect of G2. Now here if you see, G2, G3 are in cascade fashion, and for this G4 is also getting added, and G2, H1, G2 are also in cascade fashion. So now the block is completely reducing. You can observe the block is completely reducing. So this particular block, how it is reducing is G2, G3 plus G4. So the entire block is reduced as something like this. So this entire block is reduced something like this. These two also reduce directly, H1, G2. So this is directly connected at the C, and there is one summation block here that is connected here. This is plus and this is minus, and this is H2, right? Yeah, H2. There is block called H2 here, right? Now there is another block called G1 here in between. Okay, so there is again one plus and minus here, and so there is from here there is H1, G2 is coming to touch this particular point, and obviously the R is there here, plus minus, the R is coming here, and this is how you can take that into picture. Now here one simple thing that we wanted to again modify. There are so many ways to modify it, okay, obviously. So here, suppose if I bring this to this will be coming in the form of G by 1 plus GH form. Okay, so or you can move these summation blocks to this. Whatever you want, you can do it. Suppose if you move the summation block, there is a possibility that you can move that this particular summation block to here. When you move the summation block, the effect of G1 will be nullified. So that effect of G1 we have to take into consideration. Earlier the effect of G1 is there. When you move this summation here, the effect of G1 will not be there. Okay, so that the effect of G1 has to be removed. So now when I am bringing this to this, okay, when I am bringing this to this here, this effect of G1 whatever is there, that I have to multiply in the denominator of this 1 by G1. So 1 by G1 into H2 will become H2 by G1. So I am just making one more step so that you can understand it clearly. So here same, your R is there, plus minus is there, and then there is one more summation, plus and minus, and here there is a function called G1 is there. So now this particular item we have transferred here, right? Okay, so this G1, so when we transfer this the G1 will not be coming. Okay, so what is coming here? When we are transferring, the summation block is coming here. Summation block is coming. After summation block, the G1 is coming. This G1 is in directly get in touch with G2, G3 plus G4. Now this is happening. Now in this feedback, so earlier what was happening here G1 is coming into picture. Here G1 is not there. Now when G1 is coming here, I have to divide the effect of G1 here for the H2, because now the G1 effect is coming, right? That's why. That's all. That's all. Now here, as it is, your H1 Z2 will be there as it is. And main your this particular thing obviously there. This is R, this is C. So that is how I can try to do the things very carefully. Now let us understand it in a very thorough fashion. Okay, so now these are the so many feedback things are there. That feedback things we have to eliminate one by one and make it as a proper block diagram. Okay, so firstly, so we have done this way. Here one important thing is coming. This particular point is forming a path and this particular point is forming a path. So these summations are, if you try to interchange the summation, then what happens if this summation is coming here and if this summation is coming here, so this will form one path and this will form another path, G by 1 plus GH form. So that's all, like we have to slightly interchange the summation path, and then what is happening, let us see. So if I bring this to here, what are the effect? If I bring this to here, what is the effect that is coming? Okay, so now let me write as it is, that is Z2, Z3 plus Z4. This is not changing. Okay, this is connected at the output C. This is connected at the output C. Now what I am doing, I am bringing the summation path here. First summation path. The first summation path is G1 is there. For this G1 and this summation path I am removing, I am bringing this to here, right? When I am removing, for the effect will come into later. Now if I bring this here, this G1 H1 Z2 will form a path, right? So like G1, whatever the effect G1 is coming, the summation, and since I brought the summation here, this will just become G1 H1 Z2. Similarly, this summation I am bringing it to here, right? So at the time, this H2 by G1 is coming to this particular summation path. That's all simple it is. Very simple. And this is coming to one more summation path. Now this forms one particular G by 1 plus GH form. This will come as one block diagram, and this and this and this will be in cascade. So this forms one more block diagram, and this all everything is coming in 1 by GH plus form. This is coming as one transfer function. Again this will come as 1 by 1 plus GH form. So like this you can bring down that to your way of think. So one more time, I'm just telling you. Firstly, this particular item, whatever this you are seeing here, it is G and H. So suppose if you assume G and H, this will come as G by 1 plus GH form. So as something one block. Now this is in cascade with this. So now this and this will be multiplied. Say this is say G1, this is say G2. These two will be cascade and these two all will come into one particular block, that is say G1, G2. Now this G1, G2, let me assume again as G. This is in with again H. Say this is again G by 1 plus GH form. So this all will come as G by 1 plus GH form. G by 1 plus GH. Now again this is I am assuming as G. This G and H is 1. Again this will come as a function. So that is how you can bring down the entire block diagram reduced like anything. So this is this is how we can generally reduce the block diagram using block diagram reduction technique. But people has gone far more ahead and they propose a lot of other technique to reduce the block diagram scheme. So I'm just going to discuss that in the session number 7. How can just by seeing the block diagram, how can we make a transfer function instead of making so many block diagram reduction? That can be done using with the help of our Mason-Gain formula that generally also equally correct as per this